Hello, welcome to the start of Unit 2 in Advanced Pre-Cal Polynomials. This is the set of notes that goes with determining the x-intercepts of quadratics. For us right now, quadratics have two different forms that are of use to us. That being the standard form of a quadratic equation and the vertex form of a quadratic equation. You'll notice that the coefficients matter in each case, and they mean something, and the other variables in the vertex form of a quadratic matter as well. The standard form over here on the left is a useful form to factor. We like to factor from this form. And then the vertex form is a useful form to graph. It's easy to see the transformations. It's easy to see the vertex. HK is really easy. This is the vertex. The x and the y coordinates of the vertex are HK. So we'll be using that a little bit more. Back over with the standard form of the quadratic, we'll be using this a little bit more today. A is always the leading coefficient because it has the highest degree in the quadratic, and when it comes to leading coefficients, the leading coefficient is always paired with the highest degree. B is the coefficient on the first degree term, and C is on the constant term, which has a degree of 0, by the way. Cx to the 0. And for our vertex form of a quadratic, x-intercepts can be found if f of x or y is set to 0. So it's a little bit longer of a solution if you choose to go that route with vertex form instead of just factoring. If you want to go in between these forms, this is something that we'll talk about later on, but you're going to complete the square to get over to vertex form if you start with standard form, and you will multiply out this vertex form in order to get back over to standard form. Now, a lot of pre-cal is flexibility in being able to solve an equation from any position. So these are all quadratics, 1 through 4, but you're asked to solve the equations by factoring. If an equation cannot be factored, we're going to use the quadratic formula. And just to be clear what that is, negative b plus or minus radical b squared minus 4ac all over 2a is the quadratic formula, and that helps us solve for zeros if an equation cannot be factored. And we have some ways of determining if an equation can be factored easily. So we'll just start off with number 1. Number 1 has a standard format of our quadratic equation. So we're just going to double check our AC method. And if you remember the AC method, we take 2 and 7 and multiply them together to get 14. What are the factors of 14 that can produce 8? Can we do that? We've got 2 and 7, and we also have 14 and 1. And we cannot get 8 from that. There's no way we can add 2 and 7 or subtract 2 and 7 from each other, or 14 and 1, or any combination within these two sets, so that we get 8 as our middle coefficient, b. So we have to use the quadratic formula. So this is just as easy as recognizing that 2 is a, 8 is b, and 7 is c. So we'll plug through this real quick. If we do this correct, then we will get 2 solutions of our quadratic. And you probably recognize from Ms. Tackett's video that you'll get 2 solutions usually, unless the vertex is the only point on the x-axis. Alright, so I would be cautious of using a calculator straight away here, because things like the ACT and R tests are going to ask you to maybe find a solution that looks like this. So they're forcing you to use the quadratic formula to make sure your answer is in that format. So that's what I got for number 1. Make sure you can get there as well, just by operating through those functions. And we do get 2 solutions. Number 2 is a vertex form of a quadratic. So I'm going to multiply this out. X squared minus 12x plus 36. So I'm really good at multiplying binomials out. Make sure you know that this is x minus 6 times x minus 6. And you double the middle term, you multiply the last 2 coefficients, the last 2 numbers in the binomial together to get 36. And you can multiply that out really fast. And this ends up being my quadratic. So can we find the AC, with the AC method, factors of 39 that can add together to be negative 12? So we've got 13 and 3. Ooh, it looks bad, because 13 and 3 are both prime, and 39 and 1 are not going to work either. So we'll also have to put this one through the quadratic formula. Alright, so already we have a tough situation here. In the radical, we're going to have a negative number, so there is no real solution. To this quadratic. And if you notice, if you were to graph this, then the parabola is lifted off 3 units from the x-axis and shifted right 6. So clearly there are no intersections with the x-axis. And this is it's really important that before we start factoring, because this almost looks like standard form, that we factor out the common factor. So the common factor here is negative 1. So I get x squared minus 6x plus 8. And this actually ends up helping us a lot. We can disregard this negative 1 when we start solving for the x-intercepts, because I know we've had 2 examples of using the quadratic formula, but when you factor a quadratic, you set the y value, which is f of x, you set the y value equal to 0. So we really only need to solve x squared minus 6x plus 8, because we can remove this negative 1 by dividing each side of this equation by negative 1, and away it goes. That negative 1 does not influence the zeros. So with the AC method now that we've gotten our greatest common factor out, what 2 numbers add to be negative 6 but multiply to be 8? So it looks like we've got negative 4 and negative 2 will work out. They do. So 0 is equal to my factorization here, minus 4x minus 2, and then my zeros, or my x-intercepts, x equals 4 and x equals 2. So that would be my final answer. Be aware that we might ask for the factored form of this quadratic, in which you would respond with the two binomials multiplied together. Alright, lastly, number 4. This is a quadratic because we can see the second degree, but it's not written in a very familiar way. However, we can still factor it to find zeros. And I already know just from context clues and what I know about transformations, so I'm using those context clues, is this is a parabola that's been moved up 16 but reflected across the x-axis and shrunk vertically. So the graph looks wider because we've shrunk it. So I know that these lines will eventually get to the x-axis and they'll cross it so that we have zeros. And another thing that I remember about factoring is that there are special types of factoring. For this equation, I'm recognizing a difference of squares. If you're not comfortable with recognizing that, you can obviously use the quadratic formula, or you can use what a difference of squares factors out to be. So what's the square root of 16? That's 4. What's the square root of 1/4 x squared? That's minus 1/2 x. And then we'll take the positive version of 1/2 x, the conjugate of what we just wrote. So when I multiply these two binomials back together, I will get the original equation. And to solve, I'm going to set this factor, 4 minus 1/2 x, equal to 0. And I'm going to set 0 equal to 4 plus 1/2 x. And so I'll solve it that way. So I'll get 8 equals x, and then I'll get negative 8 equals x. You could probably see a different way to solve this one. If you subtracted 16, you can, this is actually in, this equation is actually in vertex form. It just takes a little bit of rewriting it. You can actually set this equal to 0 and solve for x as well. So there's multiple ways you can find these solutions. But really, there's only one way to find the factored form. So know that that part of this is unique. Right, so if you're in advanced, then there's a second part to this video. Right, so if you're in the advanced class, then you have a little bit more to do. This is U substitution. And this is a way to factor, it's a way to rewrite something that is complicated so that it can be recognized in a simpler method. So here we're going to use U substitution to factor. What I've written here in the middle, this is the composition of functions for quadratic with U as the variable instead of X. So the whole goal of factoring using U substitution is to find to make sure you're looking at a quadratic form of your equation. So if we take this example over here on the right, it's actually the easier one. How can we find how can we make this function look like it is built as a quadratic? So in other words, what would you make u? How would you compose a function inside of this pink function with all the u's in it, so that it looks like x to the fourth minus 4x squared minus 5. So u in this case would be x squared. So I would take x squared and say u squared minus 4u minus 5 is equal to 0. And I would solve this quadratic by factoring. So I've just replaced everywhere I found an x squared, which is, I found 2 of them here, that's why it's u squared, and I found 1 of them here, that's why it's just u. I would replace them with u. And by factoring, I'm going to get a pretty easy factoring solution: u minus 4, u minus 1, and then my zeros for u is going to equal 4 and u is going to equal 1. But that does not mean that the x-intercepts are 4 and 1. That means that u's intercepts are 4 and 1. We have to go back and replace u with 1 and 4, or u with x squared, so that they equal, so that x squared equals 4 and 1. So to finish this off, we actually have x equaling plus or minus 2 and x equaling plus or minus 1. You can go back and factor this polynomial, or sorry, graph this polynomial, and check to see if those are the correct solutions. They are. But that's how you're going to use u substitution. Here, in this more complex example, what are we going to make u? Whoa, that was strange. What are we going to make u so that this function looks like it fits the quadratic form, this pink quadratic form right here? It looks like we can make u x plus 3, but then we still have a degree of 6 and a degree of 3 on these terms. So we're going to make I don't know, I had to square there this whole time. We're going to make x plus 3 cubed be u, so that when we replace x plus 3 cubed, we should get a really simple quadratic form. We should get negative u squared plus 4u plus 21. So we have replaced x plus 3 cubed with u. And then factoring this, it's not so bad. Factor out a negative, that goes away. So u is equal to u squared minus 4u minus 21. The AC method is saying we've got 7 and 3, so negative 7 and 3. So u minus 7 and u plus 3 equals 0. So that's not so bad. Factoring this isn't so bad. U is equal to 7 and u is equal to negative 3. And to round this out, we have a little bit trickier of an equation to solve. U was equal to x plus 3. So x plus 3, well, it was x plus 3 cubed equals 7, and x plus 3 cubed was equal to negative 3. If you know something about undoing a cubic, you would just take the cube root, and cube roots are great because it doesn't matter if there's a negative under the radical, you can still solve it. But this is what you should get for your solution. And I'm leaving it not as decimal in its most accurate form, and you can do that as well. Alright, so there you go. I've got my solution for this equation.